Let's take a look at how we would approach solving ether reaction practice problem B. In this particular example, we have a cyclic ether, a ring with the oxygen in it, and that oxygen has carbons that are fairly highly substituted, specifically tertiary, on either side of it. We're reacting it with hydrobromic acid. Now, as a general strategy when we're doing these acidic ether cleavage reactions, is that we're going to split that ether into two pieces by replacing the oxygen attachment to both carbons with bonds to our halogen. So what we'd see as a product then, we'll draw the ring nice and big so that we can include or separate those two carbons. We'll put a bromine on each of those carbons that used to have the oxygen. Now, in terms of a mechanism, we're going to clear out some space here so we'll have plenty of room to work. And we'll start with our HBr and our ether. The first thing that we're going to do, of course, in any reaction involving a strong acid, have the acid do the acid thing and donate a hydrogen to our ether. So our HBr gives up a hydrogen, and that protonates our oxygen. The reason that we're doing this is to make that oxygen a good leaving group. Remember when we converted alcohols to alkyl halides, that we needed to make the oxygen a good leaving group. Remember also that we say no O- in acid. We're in acid, and so when we have one of these oxygen carbon bonds break, doesn't matter which one because of the symmetry, we'll just take this one because it's easier to get to. When that carbon oxygen breaks and the oxygen keeps the electrons, the oxygen now will become neutral. If we did not pre-protonate it, we would of course be making an O-, and again, no O- in acid. So this gives us a tertiary carbocation. So we're doing this as an Sn1 or an Sn1 reaction because we are under protic conditions, and we can make a nice stable carbocation, specifically the tertiary one. So now our bromide comes in, we attach that to the carbocation. So first step, leaving group leaves. Second step, nucleophile attaches. Sn1 and E1 are unimolecular. The carbocation is formed. Now we have got one of our bromines incorporated into our molecule, and we simply need to get the second one in. Now remember, these reactions only happen in the presence of strong or concentrated acids, and so that means that we are to assume that we have enough HBr around to react a second equivalent. In this case, because our second carbon is also a tertiary carbon, we're going to do another Sn1 reaction. In this case, we're simply converting an alcohol to an alkyl halide, which is an org-1 reaction, and it's basically what we just did, only we're using water as a leaving group rather than the alcohol from when the ether broke up. Now let's make sure, as we're redrawing our ring, that we have the right number of carbons, right? So our tertiary carbon, then 1, 2, 3, and then our second tertiary carbon, 1, 2, 3. So it's easy in this case to miss a carbon. Now that we've prepared our leaving group, we can break away that leaving group to give us our carbocation. And now we have another tertiary carbocation, And it also gives us, we're just going to put our 1, 2, 3 carbons, then our tertiary carbon here off to the side to give us more room. The water leaves, so we've produced an equivalent of water, and the bromide that was produced when we protonated that oxygen now can come in as a nucleophile and attach, and we have now completed our mechanism. We have our product, 1, 2, 3 carbons, next tertiary carbon, which would be 1, 2, 3, 4, 5, 6, 7, 2, 6 dibromo, 2, 6 dimethyl heptane.